Every second of your life, your heart performs a miracle you never see. Deep inside the left ventricle, the most powerful chamber of your heart, thick muscular walls contract with precise rhythm, generating the pressure that will send oxygen-rich blood to every corner of your body. This isn't a metaphor. This is the real biological engine that keeps you alive, squeezing approximately 70 milliliters of blood upward with each beat, and it never stops. Not when you sleep, not when you dream. This chamber will beat over 2.5 billion times in an average lifetime, and right now, it's beating for you. The journey begins as blood surges from the heart into the aorta, the body's main highway, at nearly 3 feet per second. You're looking at the very moment life-sustaining oxygen begins its delivery route. And these aren't special effects. Every red blood cell you see is real, tumbling through the current, each one carrying millions of oxygen molecules bound to hemoglobin. The aorta's walls aren't rigid pipes. They expand with every heartbeat, absorbing the pressure and creating a smooth, continuous flow. And this elastic property protects your delicate organs from damaging pressure spikes. Without this flexibility, your circulatory system would fail within minutes. Now we're witnessing something most people never consider: your heart muscle feeding itself through coronary arteries embedded deep within the cardiac tissue. Because your heart can't absorb oxygen from the blood passing through its chambers, it needs its own dedicated blood supply. Block one of these vessels, and the muscle downstream begins to die within minutes. This is what happens during a heart attack. And the three-layered wall you're seeing, the smooth inner lining, the muscular middle layer, and the protective outer coat, is what keeps blood flowing even under immense pressure, flexing with every heartbeat. Because they're not just tubes, they're living, responsive tissue. Here's where the magic of life happens at the smallest scale. You're looking at red blood cells squeezing through a capillary so narrow, they must deform their shape to pass through single file. A vessel only 7 micrometers wide, 70 times thinner than a human hair. And this is where oxygen delivery actually occurs. The capillary wall is just one cell thick, allowing oxygen to diffuse directly into the surrounding heart muscle tissue. And your heart has billions of these microscopic vessels. Damage this network through high blood pressure, diabetes, or smoking, and your heart literally suffocates from within, which is why cardiovascular health isn't abstract. It's happening right here, right now, at the cellular level. Blood returns home to the right atrium, where deoxygenated blood from your entire body converges before beginning its journey to the lungs. And the darker maroon color isn't Hollywood drama. This is what blood actually looks like when it's given up its oxygen to your tissues. 2 large vessels, the superior and inferior vena cava, pour blood into this chamber like rivers meeting at a delta. And here's something remarkable. Your body produces no new blood. The same 5 to 6 liters you have right now will circulate through your entire system roughly once every minute for your entire life. And there is no synthetic substitute that can fully replace human blood. This makes cardiovascular health not just important, it makes it irreplaceable. The pulmonary artery carries oxygen-depleted blood toward your lungs, and this is the only artery in your body that carries deoxygenated blood, a critical exception to the rule. Notice how the vessel branches, dividing again and again, distributing blood to millions of tiny air sacs in your lungs. This branching pattern isn't random. It's an elegant solution to a complex engineering problem: how to expose maximum blood volume to maximum air surface in minimum space. Because your lungs need to oxygenate your entire blood supply every single minute, and this vessel network makes that possible through pure biological architecture. This is where breath becomes life. We're inside the alveolar capillaries, wrapped around tiny air sacs in your lungs, and you're watching the precise moment oxygen crosses from air into blood. These capillaries are so delicate, so thin, that only a 2-cell barrier separates the air you just breathed from your bloodstream, and red blood cells press against these walls like packages at a loading dock, picking up oxygen molecules and releasing carbon dioxide waste. This exchange happens passively through diffusion. No pumps, no active transport, just the elegant physics of molecules moving from high concentration to low. And it occurs in less than 1 second per red blood cell. Your lungs process the entire blood volume of your body every 60 seconds. Now we're seeing the molecular transformation that makes human life possible. Oxygen molecule. Now we're seeing the molecular transformation that makes human life possible. Oxygen molecules drift across the membrane barrier into a red blood cell, where hemoglobin molecules immediately bind them, and watch as the cell's color shifts from dark maroon to brilliant crimson red. This color change isn't cosmetic, It's chemical evidence of oxygenation, and each hemoglobin molecule can carry 4 oxygen molecules, with each red blood cell containing about 270 million hemoglobin molecules. That means one single red blood cell transports over 1 billion oxygen molecules, and you have roughly 25 trillion red blood cells in circulation right now, creating an oxygen delivery system of incomprehensible scale. Fully recharged with oxygen, blood returns to the left atrium through 4 pulmonary veins, and these are the only veins in your body carrying oxygen-rich blood, another elegant exception in your circulatory design. Watch as 4 separate streams converge and mix in this chamber, and the bright crimson color confirms successful oxygenation. This blood is now ready to fuel your entire body. The atrium contracts, pushing blood through the mitral valve into the left ventricle below, and this valve is a one-way gate, beautifully engineered flaps of tissue that prevent backflow, because in circulation, blood must always move forward. Any reversal means system failure. We're racing through the aortic arch now, one of the most critical curves in human anatomy, where the aorta bends and gives off 3 major branches: the brachiocephalic artery, the left carotid artery, and the left subclavian artery, vessels that feed your brain, head, neck, and arms with fresh, oxygenated blood. This isn't just plumbing, this is prioritization. Your body ensures the brain receives blood first, before any other organ, because your brain can survive only 4 to 6 minutes without oxygen before permanent damage occurs. Every curve, every branch point, every vessel diameter has been refined through millions of years of evolution to deliver blood exactly where it's needed, when it's needed, in the precise quantities required. Inside the carotid artery, ascending toward your brain, blood travels upward against gravity, propelled solely by the pressure generated by your heart's contraction seconds ago. This is the miracle of hydraulics in living tissue. The arterial walls here are thick and muscular, designed to withstand and regulate the intense pressure needed to push blood up to your brain. And with every heartbeat, these walls expand slightly, then recoil, maintaining steady flow. Your brain weighs only 2% of your body weight, but consumes 20% of your oxygen supply. It's the most energy-demanding organ you have, and it cannot store energy, which means it depends on constant, uninterrupted blood flow every single second of your life. Now we're inside a cerebral capillary, navigating the blood-brain barrier, one of the most selective biological filters in existence. Red blood cells deform as they squeeze through these incredibly narrow passages, delivering oxygen directly to neurons and glial cells that surround the vessel. The capillary walls here are special, with tightly joined cells that prevent harmful substances from entering brain tissue while allowing oxygen, glucose, and essential nutrients to pass through. Your brain contains approximately 400 miles of these capillaries, creating a delivery network so extensive that no neuron is more than a few cells away from its oxygen supply. And any disruption to this flow, a stroke, causes brain cells to die within minutes, which is why we say, time is brain. Deep in your leg, inside a large vein, blood pools momentarily before beginning its return journey to the heart. And notice the venous valves, delicate pocket-like structures that hang downward like gates. These prevent backflow and ensure blood moves only toward the heart, even against gravity. When your leg muscles contract during walking, they squeeze these veins, pushing blood upward past each valve, which then closes to lock into progress. And this is why prolonged sitting or standing can cause problems. Without muscle contraction, blood pools in the legs, valves weaken, and you develop varicose veins. This system depends on movement, on activity, on your body working as an integrated machine where every part supports the circulation that sustains every other part.
Raveling through the superior vena cava, we're following blood's final approach back to the heart after completing its circuit through your body. This blood has given up its oxygen, collected carbon dioxide waste, and now returns darker, almost maroon in color, ready to be recharged. The vessel walls here are thinner than arterial walls because venous blood operates under much lower pressure, no longer driven by the heart's direct force, but pulled along by the negative pressure created when the heart expands. Approximately 70% of your blood volume sits in your veins at any given moment, creating a reservoir that can be mobilized during exercise or stress when your body needs to increase cardiac output instantly. Inside the muscular wall separating your heart's left and right ventricles, we're witnessing the heart from the inside out. This thick septum prevents oxygen-rich and oxygen-poor blood from mixing, maintaining the separation essential for efficient circulation, and embedded throughout this muscle are the heart's own blood vessels, the coronary circulation we saw earlier. Both ventricles contract simultaneously with incredible synchronization, the right side pumping blood to your lungs at lower pressure, while the left side pumps to your entire body at much higher pressure, yet both chambers eject exactly the same volume with each beat. This coordination isn't controlled by thought, it's automatic, electrical, generated by specialized pacemaker cells, and it continues whether you're conscious or not, awake or asleep, every moment from before birth until death. At the microscopic level inside a cardiac muscle cell, we're seeing the molecular machinery of contraction. Sarcomeres, the basic units of muscle tissue, shorten as protein filaments slide past each other, powered by energy from densely packed mitochondria surrounding every fiber. Your heart muscle cells contain more mitochondria than almost any other cell type in your body. Because they need constant, massive amounts of energy, your heart never rests, never gets a break, and these mitochondria work continuously to fuel every single contraction. This is why your heart is so vulnerable to anything that disrupts energy production. Lack of oxygen during a heart attack, toxins from excessive alcohol, deficiencies in essential nutrients. When energy production fails, contraction fails, and when contraction fails, circulation stops. Deep in your abdomen, blood flows through the descending aorta, branching off at regular intervals to feed your abdominal organs, the kidneys, liver, intestines, spleen, each receiving precisely calibrated blood flow based on their metabolic needs. The aorta descends along your spine, protected within your body's core, pulsing with every heartbeat as it distributes oxygenated blood throughout your torso and eventually into your legs. This vessel will carry blood for decades, its walls constantly adapting to pressure changes, repairing microscopic damage, remodeling in response to exercise or disease, and the health of this single vessel, whether it remains flexible or becomes stiff with atherosclerosis, largely determines your cardiovascular future. Entering the mesenteric arteries that supply your intestines, blood flow increases dramatically after you eat because digestion requires massive amounts of energy. Your intestines need extra oxygen and nutrients to absorb the food you've consumed, break it down, and transfer those nutrients into the bloodstream. Watch as the vessels branch repeatedly into smaller and smaller arterioles, creating a vast network that surrounds every inch of intestinal tissue. And this is why your body redirects blood away from your muscles toward your gut after a meal, why you feel sluggish after eating. Your cardiovascular system is dynamically adjusting its distribution priorities based on real-time demands. Inside the intestinal wall, wrapped around the finger-like villi that absorb nutrients, we're seeing the capillary networks where digestion meets circulation. Glucose molecules, amino acids, fatty acids, vitamins, minerals, everything you've eaten and broken down now crosses from intestinal cells into the bloodstream. These nutrients will travel directly to your liver first, through the portal vein for processing, filtering, and distribution, and then circulate throughout your body, feeding every cell, fueling every process. This is why nutrition matters for heart health. The quality of nutrients entering your bloodstream here directly affects your arterial walls, your blood viscosity, your cholesterol levels, your inflammation status. Cardiovascular disease begins not just in your arteries, but at your dinner table.